Hello, everybody. We're going to go ahead and get started with today's lesson or today's review. And so this is going to be multiple choice questions B for the AP Physics 2 exam, Unit 2. Let's go ahead and get started. Here we have a piston, a pressure gauge, and a temperature sensor, and probably some isolated or insulated container. A, it reads, a gas is in a sealed container fitted with a movable piston as shown in the figures, so that none of the gas escapes. The cylinder and piston are made of an sorry, I got the hiccups as usual, of an insulating material. The cylinder is fitted with pressure and temperature sensors, and the volume of the confined gas can be measured from the markings inside or on the side of the container. The gas is initially in a state with pressure PI, TI, and VI. The piston is slowly compressed and data are recorded until the gas reaches a final state with a pressure PF, TF, and VF. A graph of the pressure as a function of volume is shown, with dotted lines indicating isotherms. So here we have an isotherm. Here we have an isotherm, and we may be trying to remember, well, what does that mean? Well, an isotherm is a plot of constant temperature. And so the question reads, which of the following describes the energy transfer process that the insulation prevents? And so we don't have any participants today, so I think today's lesson will go by a little bit faster since we won't be polling anyone. And so if we look at this, because it's insulation, we don't want any heat entering or leaving the system. So we're going to want to try to find out which of these statements is saying that. So friction between the gas molecules moving along the inner surface of the cylinder transfers energy through the cylinder to the air molecules that move along the outer surface of the cylinder. So this sounds kind of good because, we know that friction usually creates heat. But the important thing here to remember is that the way heat is transferred is by the collisions of particles with other particles and that pass on that collision through vibration or other collisions, kind of like a pile up of cars, if you will. And so the same thing here, we're not going to concern ourselves with electromagnetic waves produced by the motion of electrical charges. Convection currents, because it is sealed, that won't be the case. And then, so our best answer choice here is going to be D. Collisions of gas molecules with the inner surface of the cylinder cause disturbances of molecules of the insulating material that travel through the cylinder, transferring energy to the air molecules that hit the outer surface of the container. So in the example that I gave for this kind of car pileup or domino effect is for energy being transferred into the system. But the same could be said on the way out. These guys collide into the walls of the container, they collide with each other, jiggle, and they pass the energy out to the surrounding environment when air molecules happen to become in contact with the walls of that container. So these are best answer choice. Let's go ahead and look at the next one. So it's the same setup as before, pressure, temperature sensor, there's a plot of the pressure and the volume. And the question reads, which of the following claims identifies the change in internal energy of the gas between its initial and final states and describes the corresponding changes in energy due to work and heating? And so if we remember, the change in internal energy is represented by the variable delta U, and we have learned that delta U is proportional to delta T. So here, if we look at our plot, we start out with some initial temperature and we finish with some higher different temperature. Remember that temperature increases as we move away from the origin here. So if I either move along this direction or along that direction or a combined effect, I'm going to increase my temperature, or my gas is going to experience a higher temperature. So it's going to be one of these two, A or B. And so the first one says energy is added to the gas via work and none is lost by heating. Number 2 says energy is transferred out of the gas by heating, but a larger amount of work is added to the gas via work. Okay. So if we look at this scenario here, we're changing our volume by about 2 counts, And it looks like we're changing our pressure by about 3 counts here. Now, the important thing here is, well, how do we compare these two quantities? Because, we've learned that work is P times delta V, and then they're telling us that here, the energy transferred out is transferred out by heating, and a larger amount is added by the gas. So how do we know if these two quantities are actually as they say here? Well, the important thing for us to understand is that this piston here is made out of an insulating material, which means that no energy will be transferred by heating. So insulated equals no energy transfer by heat transfer. So A is going to be our best choice here. Let's go ahead and look at question number 3. Which of the following claims correctly indicates the changes in the collisions between the gas molecules? Indicates the changes in the collisions between the gas molecules on the cylinder wall that contribute to the change in pressure of the gas as it goes from initial to final state. And so hopefully you recognize, well, the pressure is going to change. It's going to increase here. And so let's go ahead and read. The first part of these sentences all look the same, so I probably wouldn't worry too much about what they're saying. It's not going to make a difference. We'll assume that they're all saying the truth. Really, the second sentence where things are different. The average speed of the molecules remains the same, so the average impulse of the collisions does not change. Well, if we remember, the speed of a gas is proportional to the square root of T, or what we could say is V squared is proportional to T. The kinetic energy of a particle, of a gas particle, is basically going to give us the effective temperature. All these particles together, their average kinetic energies will lead to the effective temperature. So not the case. The next part, the average speed of the molecules increases. Well, the temperature did increase. So I do agree that the kinetic energy, or the average speed, sorry, of the molecules increases. And so we're either with B or C, or sorry, B or D in our answer choices. And they tell us, so the average impulse of the collisions increases, okay? The average speed of the molecules increases, so the average impulse of the collisions increases. Wait a minute. Okay, no, they weren't exactly the same. Here we go. One of these is telling us that the number of collisions decreases per time. Well, if we're making this thing smaller, if we're decreasing the volume, these guys are going to have less space between them to travel before they collide. So because the distance between us gets smaller and we're moving faster, we're more likely to have more collisions over time. And this will increase the average impulse. If we forgot what impulse is, so force times time is usually how we calculate impulse. It's really time interval, but whatever. And that is equal to the mass times the change in velocity, or the change in momentum. Impulse is the change in momentum, or we could say mathematically, force times time interval equals mass times change in velocity. Let's go to number 4. We have a PV diagram, and our pressure is going to vary from PA to twice that value at B and at C. And then when we go to D, the pressure will return back to the original value at A, but it now has 3 times the volume. And it reads, a sample of an ideal gas is in a sealed cylinder with a movable piston and is initially in a state A, as shown in the graph of pressure as a function of volume. The gas's temperature, state A, is 300 Kelvin. The gas can be taken from state A to state D via 3 separate paths. We can go we can go from A straight to D. We can go from A to B to D. Or we can go from A to B to C to D. And the question is, for which, if any of the paths, if any, is the change in internal energy going to be the greatest? So which of these is going to give us the greatest change in internal energy? And so to get the change in energy from A to D, or the change in internal energy as we go from A to D, Well, that's just going to be really dependent or proportional to the change in temperature. Because if we look at the internal energy formula, there's a factor of 3/2 or 5/2, depending on the scenario, times some specific heat capacity times the change in temperature. So really the important thing here is going to be the change in temperature as we go from A to B. I'm sorry, A to D. Now, one of the big things that we can try to remember conceptually is the concept of a state variable. And a state variable like temperature is called that because it doesn't matter how you get from one point to another. What the value only cares about the distance between them. We say it is path independent. 1 second. Alrighty, sorry about that. Okay, so what this tells us is that the temperature, the change in internal energy is really just going to depend on the temperature at D and the temperature at A, and how we get there doesn't really matter. So it turns out none of them is the best answer. They all experience the same change in internal energy for the 3 paths. I think I'll just change the color up this way here just for people. State variables are path independent. They only depend on this like the final state values. And because we're all going from the same point to the same, from A to D, doesn't really matter. Let's go ahead and look at the follow-up question. So it is the same scenario as before. We are told that the temperature in state A for the gas is 300 Kelvin. And they ask, what is the temperature of the gas in state B? And so if we notice, the process that takes us from A to B, and again, it really doesn't matter which path we take, because here we can go ahead and we can see that we can use the pressure and temperature, because PV equals nRT. Well, what is constant? The volume is constant. The number of moles is constant because it is sealed. And the universal gas constant is also. So what we could say is the pressure is proportional to the temperature, or the temperature is proportional to the pressure. Well, if we look at the pressure here, it is twice the value of the pressure at A. So the temperature is going to go in and increase by the same proportion. Question 6. Sorry, I'm trying to fix the microphone here so that it can pick me up and not the lawnmower in the background. Question 6. In this, sorry, 1 second. Okay, so in question number 6, they ask, in which process is energy transferred from the gas to the environment by heating only? And so this can seem pretty overwhelming. We may not know, okay, well, how are we supposed to think about it? Well, this is where the second law, or sorry, the first law of thermodynamics comes in handy. So one way to rewrite the law of conservation of energy is the change in the internal energy of a gas or a system or some kind of material is equivalent to the heat added or the heat transferred plus the work that we do on the gas. If I compress this gas, if I do work on it, it's going to get hotter. That's one way to think about it. If I add heat to it, it will also get hotter and change the internal energy. So here we want to find out the energy, the process in which energy is transferred from the gas to the environment by heating only. Now we have to be careful here. What they mean by that is that this is the only process that allows energy to be transferred. No work on or by the gas is allowed in this case. So what this is really telling us is that the work is going to be 0, either the work by the gas or the work on the gas. Basically, we have to find a scenario where there is pure heat transfer. And if we remember, work is given, and there's a negative in here, and we're not going to worry about it right now, but the magnitude of the work is given by P times delta V, whether there's expansion or compression, there's going to be work. If delta V happens to be 0, then that tells us that the work on or by the gas, doesn't matter in this case, either way, is going to be 0. So automatically, if we notice, process A and B are going to be are going to be our most likely candidates. So let's go ahead and cancel out, I guess, B and C, B to be C, and then BD, which leaves us with just these two. The next part here is, well, we need to find a scenario where heat is transferred from the gas to the environment. So the first law of thermodynamics says that Q is positive if the heat is added to the gas, and Q is negative if it is lost. If heat is lost by the gas or the system in question, then the sign for Q will be negative. So kind of putting some ideas together, we've learned that delta U, in this case, will then be in proportion or have the same sign as the Q. So we're looking for a scenario where heat is removed, which is going to make Q added be negative. Well, that tells us that delta U is going to be negative in this case. If we're losing heat, another way we can think about it is the gas is cooling. The gas cools off. It drops in temperature. So delta T is going to be negative. So we're going to lose temperature. And the process that shows us losing temperature is, well, let's see here. I have an isotherm like this at C. I have an isotherm essentially like this at D, through B and D. And then I have an isotherm, oops, let's go back. An isotherm passing through A. And I mean, there's continuously many isotherms, but I just kind of drew the main ones of interest. So if we go from A to B, delta T from A to B, or for A to B, is going to be positive. If I go from state C to state D, the temperature decreases. So the change in temperature from C to D is going to be negative. And so there's our answer. C to D is the process by which we give heat to the surroundings if we are the gas. Go ahead and look at number 7. The graph shows pressure as a function of volume for a sample of an ideal gas that is confined in a cylinder. A movable piston sits on top of the gas, and the piston can move vertically with negligible friction. The weight of the piston is significantly less than the force exerted by the gas on the piston during the process shown. Which of the following is true of the acceleration of the piston during the process? And so the wording of this problem here, and I'll put it, is a little misleading. Because if we notice, we're going to have a pressure and an expansion, and they tell us that the weight of the piston is significantly less than the force exerted by the gas. So a very common answer here is for people to say either that the acceleration itself is increasing or it is decreasing. Now, let's go ahead and try to consider Newton's second law and this piston. Oops. So in this case, come on, one note. This piston has some kind of weight pulling it down. And then we have some force from the pressure pushing it up. Because if we look, the pressure or the volume here is expanding. So I'm going to go ahead and draw the force from the gas. Now, if we look at this, well, Newton's second law tells us that the net force equals ma. So net force here is going to be the force of the gas minus the weight of the piston equals m times a. So let's go ahead and look at what's happening to the force of the gas. Well, the pressure here is constant. We have a constant value for our pressure, which means that this force here is going to be constant. Everything here as well is constant. And so the acceleration here will not be zero. There is a net force from the force of the gas, but the acceleration itself will stay the same because the force from the air is the same because the pressure remains the same. In addition, the mass of the piston does not change, and neither does the gravitational field strength or the acceleration due to gravity. So D is our best answer choice. All righty, here's question 8. We have a block, some gas, and a piston. A piston is filled with gas. A container filled with gas is sealed on the top by a piston of negligible mass and area. And they give us the area. The area is, what is this? Oops, 5,000ths of a meter square, 0.005 meters squared. The container and gas are allowed to reach thermal equilibrium with the surrounding air, and the block on top of the piston keeps the piston in place. If the pressure inside the container is 300,000 pascals, what is the total downward force exerted on the piston? And so one of the key things to answering this question is that we have reached thermal equilibrium. There is no heat flowing in or out. And as far as we can tell, the piston is kept in place, which means that its acceleration is zero. It remains at rest. The velocity of this is zero, and it is constant. So this automatically tells us that the acceleration of the piston is zero. So when we consider the force from the air, or sorry, the gas is better stated. Well, that force from the gas is going to equal to the force of the block, its weight, and the weight of the piston acting down. So here, that's going to be equal and opposite to the force acting on the piston. So all we really need to do is get the force from the gas, which is going to become the area of the piston times the pressure of the gas. And so this becomes 0.0005, oops, too many zeros, meters squared times 3 times 10 to the 5 pascals. And so this is what, 5 times 10 to the negative 3 meters squared times 3 times 10 to the 5 pascals. And so this becomes, let me make that a little bit higher up here. And so the force from the gas is going to be 15 times 10 to the 2 newtons. And so that comes out to about 1,500 newtons. So C is our best answer choice. 1,500. One way we can think about it is 10 squared is 100, 15 times 100 is 1,500. All righty, let's go ahead and look at question number 9. So a cylindrical container with a movable piston contains a fixed amount of ideal gas. Initially, it is in thermal equilibrium with an ice water bath. The diagram shows the forces exerted on the piston. The cylinder is then removed from the ice water and placed in a hot water bath, and the system comes to thermal equilibrium with its surroundings. The forces exerted on the piston once the system reaches equilibrium are shown in the figure. What is the relationship between the forces exerted on the piston? So again, we are in equilibrium. The gas was probably expanding due to the hot bath, but now it has reached thermal equilibrium. The gas will no longer expand. There's no more increases in pressure, and the atmospheric pressure has remained constant, and the weight of the piston as well, the weight of the piston. So in this scenario, because it's in equilibrium, the acceleration is a big old zero. Everything has kind of reached a point of stasis. Oh man, OneNote is kind of crashing. Give me 1 second. There we go. And what we find out is, well, those two forces from the atmosphere and the weight of the piston act down, and they're going to be balanced by the force from the gas. And so B is our best answer choice. Let's go ahead and look at question 10. A gas molecule A is moving to the right with a speed v as shown in the figure. when it collides with an identical gas molecule B, which is at rest. After the collision, molecule A is moving directly toward the top of the page with a speed of v. Which of the following best represents the net force on the molecule during the collision? And so we have seen that an object accelerates in the direction of the net force. That's the vectorial part of this expression. So if we want to find the net force direction, we're going to need to find the direction for the acceleration. And acceleration is delta v over delta t. And what this tells us is we need to find the change in velocity. And so that's going to be v final minus v original. We could do a little bit of vectors here. And then we can also talk about, well, how do we arrive this probably quicker? So the final velocity is directly upwards. So we're going to go ahead and do that. This is v final. The original velocity was to the right. So then if I want to add these two, well, one way I can think about it is I'm going to take the v final and I'm going to add a negative v original to it, which is going to flip the direction. Oops, I probably drew that guy way too big. But something like this. And so our acceleration is going to be in the direction of the change in velocity. Now, here's another way we can think about it. This particle was moving to the right at the beginning. It's no longer moving to the right, so we needed a force to cancel that rightward motion. So we needed a leftward component to our velocity. Now, at the end, it's moving straight up, and at the beginning, it was just moving sideways. So we needed a force that had a component up to give it that upward velocity. And so C is going to be our best answer choice here. We need to cancel the rightward motion and add to it some upward motion. Question 11 is multiple correct. Let's go ahead and see here. A system consists of two containers containing different liquids. The system is insulated and no thermal energy is lost or gained from the environment, specifically from the environment. So maybe these two containers are inside an ice chest or something, but they're separate containers. Liquid A has a density of 800 kilograms per meter cubed with an initial temperature of 60 degrees Celsius. Liquid B has a density of 1,000 kilograms per meter cubed and has an initial temperature of 20 degrees Celsius. Which of the following statements accurately predicts what will happen once the containers are put into thermal contact? Select two answers. So these guys are actually going to be put into thermal contact with one another. And so because one is hotter than the other, the temperature at A is greater than the temperature at container B. So heat flows from A to B. So let's go ahead and see here which of these that might read. After a long time, the liquids have the same internal energy. Well, we have learned that that U, the internal energy, there's no change here. But U is equal to, or sorry, not equal to, but proportional to, we could give you the equation, but here the important thing is just recognize that it's proportional to the temperature. So this heat is going to flow from A to B until the temperature at A equals the temperature at B. So after a long enough time, the liquids are going to have the same temperature. And since the internal energy depends on the temperature, well, then they're going to have the same internal energy. Hold on. I don't like this part, actually. They're not going to have the same internal energy exactly because there's other parts to the equation here. They're different liquids. So this is a big gotcha. They contain different liquids. They may have different specific heat capacities because as it is, these are not gases. If these were gases, that would be the case. It doesn't matter what the gas is. If they have the same temperature, they will have the same internal energy. But liquids are going to have your specific heat capacities, which are like your CPs or your CVs. And so in this case, because the liquid is going to have a different CP and CV value, for between the two of them, we can't say this for sure. If they were gases, we could go ahead and agree with that. So not quite. B is the one that we were saying at the beginning. These temperatures or these liquids are going to have the same temperature after a long time because of the heat flow. And so the other answer here is thermal energy will be transferred from liquid A to liquid B. So heat flows from A to B, and heat is thermal energy. Because liquid A has more internal energy per molecule. The density has nothing to do with it. We need to transfer over, and this guy is more dense, if you will. There's more energy density, not density, but energy density in container A. Let's go ahead and look at number 12. The figure shows the movement of a fluid through an automobile engine and a radiator. The system is designed to prevent overheating of the engine. Which of the following claims correctly describes the energy transfer process involved? Select two answer choices. So if we look at this, our engine's going to get hot and it's going to transfer its heat to the cool fluid here. It's usually a gas or water. And so here, this is cool. If we look at the diagram, they're telling us that the temperature in this region is going to be a lot less than the temperature in this region. It is hot, and the reason it is hot is because it has absorbed energy from the engine. And then the radiator is going to go ahead and help remove that heat by passing air through it. And so the heat from the hot fluid was going to be transferred to the air. So let's go ahead and see here which of those is it. So thermal energy is transferred out of the hot fluid in the radiator, and the resulting cooler fluid is used to cool the engine. That's exactly what the radiator does. B, thermal energy from the air is added to the hot fluid to reduce the temperature. No, the moment we add thermal energy, T increases. We don't want to do that. So if this air here was hotter than this over here, than the hot fluid, then your engine would have a very tough time operating because it's just going to get hotter and hotter and hotter as it goes through its cycles. C, the hot engine adds thermal energy to the cool fluid, which reduces the temperature of the engine and raises the temperature of the cool fluid. There's our other answer right there. And then D is just kind of ridiculous. Okay, let's go ahead and look at 13. A sample of a hot gas is contained in a cylinder with a movable piston. The gas expands, doing work on the piston and absorbing thermal energy from its surroundings. Which of the following identifies and justifies the correct form of the first law of thermodynamics during this process? So if we look at this, the work is done by the gas onto the piston. And then it's also absorbing energy. So what's going to happen? Well, if the gas is doing work, it is losing its internal energy. It's relieving itself, if you will. So we're going to want to do, normally, delta U is written as Q plus the work on the gas. If we do work on the gas, we're energizing it. And so that's the opposite here. The work on the gas is the same thing as the negative of the work by the gas. So we can go ahead and substitute a negative here. That'll be the negative. And then Q is positive if heat is absorbed by the thing in question. So here we're wanting to draw, come up with the first law of thermodynamics for the gas. And so the gas is absorbing heat. And so A is our best answer choice. Thermal energy is transferred to the gas from the surroundings, and then the work is done by the gas. All right, here's another pressure volume diagram. Give me 1 second. The graph shows pressure as a function of volume for a sample of an ideal gas in a cylinder. Which of the following is correct about the net work done by the gas during the cycle? And so if we look at our cycle, in this case, we have expansion work. This is work by the gas. And this one's really easy to calculate. This is just going to be given by the pressure, because it's constant, times the change in volume. And we're going to go from one original volume to a final volume. And so that will give us the change in the volume. So here we have the work done by the gas. Now, if we look, this process here is an isochord. This is a zero change in volume. The volume is constant here. It has one value along that entire line. And then in the third process here, we have compression, sorry. Delta V here is going to be negative. This is work done on the gas. Work on the gas, because it is compressed. So work on the gas equals it is compressed. Work done by the gas means that it expanded. So our gas is going to do a little bit of both in each scenario. In one scenario, in one leg of the process, it expands. In the second leg, it does no expansion or compression. And then in the third process, it is compressed. And so if we want to find the work for the cycle, we learn that it is the area enclosed by the cycle. And here they want the work done by the gas. And so it is going to be the area enclosed by the cycle, because the net work done by the gas during process X, or the net work is the work done by the gas done on process X minus the work done on the gas during process Y. So there we go. It can get a little confusing because of how we define the third law of thermodynamics. One way is Q plus W, and that's if we're talking about work done on the gas. Another one is delta U equals Q minus W, and that's when we do work by the gas. Excuse me. Let's go to number 15. A cylinder is fitted with a low friction movable piston and fitted with air at room temperature and atmospheric pressure as shown in the figure. The initial volume of the cylinder is 0.2 meters cubed, and the bottom of the cylinder is placed in an ice bath as shown in the figure on the right, causing the volume to decrease to a value of 0.15 meters cubed. The atmospheric pressure is 1 times 10 to the 5 pascals. And the question is, what is the work done on the air inside the cylinder during this process? So if we look at this, we have some atmospheric pressure acting on the surface of this, and we have the pressure from the air acting against the surface from the other side. And so because this guy is going to compress, we're going to have more work done by the pressure, or sorry, the thing doing the pushing here is going to be the atmosphere. And so in this case, we can get the work done on the air inside the cylinder by saying the work is equal to P times delta V. And so this becomes 1 times 10 to the 5 pascals. The change in volume is going to be negative 0.15 meters cubed minus 0.2 meters cubed. And so this becomes 1 times 10 to the 5 pascals. And the difference here is going to be meters cubed. And so this becomes a negative 0.05 meters cubed. And so this is going to be about 5 times 10 to the, we need to move 2 over, 10 to the 5 times 10 to the 3, not 5. 5 times 10 to the 3 newtons. Now, is it going to be positive or negative? So let's go ahead and see here what the question is asking. The work done on the air. So we need to go ahead and see here. Okay, well, were we compressed or did we expand? Well, we were compressed. So because things are compressed, we're going to go ahead and take the positive here, the negative. Oh, hold on. I think I'm going to double negative myself. Work done on the gas is positive if the change in volume is negative. So no, because there's really the little negative there. And so, well, bam. It's going to be D. Almost made a mistake there. Okay. the actual, so the work done by the gas is going to be negative P times delta V, or we could say the work done on the gas equals, let me just make sure here. That increases if we're expanding. That would be positive, work done by the gas. When we put that into the thermal law, yeah. Okay, so we should just take the positive value here. Okay, so we have on this question 4 different cycles: process W, X, Y, and Z, and the ones on the left occur at 1 cycle per, or the ones on the top occur at 1 cycle per second, and the ones on the bottom occur at twice the rate, 2 cycles per second. And the ones on the left are rectangular cycles, while the ones on the right are going to be triangular cycles. And so the question is, which of the following correctly ranks the energy transferred out of the gas in a given time interval? So here they're looking for the work done by the gas. And so here is our power stroke, if you will, where we deliver power from the gas or energy from the gas to the system or the surroundings, sorry. And so if we look here, the work for this cycle, well, it's clockwise. And so that tells us that this is the work done by gas. And so that is going to be a whole rectangular area's worth of work compared to this guy. So if we look at this, the work from process W is going to be approximately twice the work from process X. But we have to be careful. In process Y, we have the same pressure difference and the same volume difference, but this time it's occurring twice as fast. So what we see here is that the work from process Y is going to be greater than the work from process W. Now, if we look at process Z, sure, it has half the area as these cycles on the left, but it occurs at twice the rate. So it turns out that the work from process Z is going to equal the work from process W. And those will be greater than process X. That Z over here looks like a 2. So I'll go ahead and write it like that. So our ranking here is going to be the energy transferred in Y is the greatest, followed by the equivalent energy transfers in process W and Z, which will be greater than the energy transfer in process X. Okay, here's our next question. We have a pressure measured in kilopascals and a volume measured in cubic centimeters. A student has a sample of gas in an insulated cylindrical container with a movable piston. The student compresses the gas by increasing the force exerted on the piston and measures the pressure and volume of the gas. The student needs to determine the work done on the gas. Which of the following describes a correct analysis of information from the graph that will determine the work? So in this case, the pressure is not constant. So when we look at the work done, like on the gas or by the gas, there's usually going to be an integral of P dV. This is the calculus or the formal way of writing it. The problem with that is, well, we don't have pressure as a function here. We don't know exactly what that pressure here is, so we can't actually integrate this. But the important thing to recognize is that the integral of something is the area of that graph with axes of pressure and volume. So chances are we're going to probably want to look for some kind of statement that states something about the area bound by this curve. So multiply the average pressure data by the average volume. Yeah, that might, well, no, because to do work, we need to have a change in volume. So this is the gotcha right here. Not going to work. Multiply the average of the pressure data by the total change in volume. Add this to the product of the initial pressure and the total change in volume. Okay. Multiply the total change in pressure by the total change in volume. And so this would be delta P, and then this would be delta V. And so that looks like that might work. That looks like base times height. Okay, let's go ahead and see if there's a better one. Multiply the total change in pressure by the total change in volume to divide the result by 2. Add this to the product of the final pressure and the final and the total change in volume. So if we look at this, the main issue is that this line of best fit for our data doesn't actually go all the way to 0. So if we really wanted to get the area, this is where we would want to get the area of this triangle. And I'm sorry, I drew my delta P all the way to the bottom. For some reason, I assumed that it would drop all the way through, but not. This part is delta P. And so we're going to get this area, but we still need this lower area down here. So we're going to want to take the final pressure value, which is the 40 kPa, and multiply it by the same base, or the change in volume here. And so I think in this case, D is going to be our best answer choice. 18. A student is sitting on the ground a few meters away from a campfire on a cool, windless night. The student feels noticeably warm on the side facing toward the fire and noticeably cool on the side facing away from the fire. Which of the following models describes the primary method by which the side of the student facing toward the fire is warmed? So let's see here. The burning wood heats the surrounding air. Some thermal energy is conducted through the air to the student. The burning wood heats the surrounding air. As the heat expands, it comes in contact with the student. The student emits radiation in the form of charged particles. Some of those particles strike the student. Charged particles. The fire emits electromagnetic radiation. Some of the radiation is absorbed by the student, converted to thermal energy. So I think D is going to be our best answer choice here, because as the student is sitting by the fire, the air that hits him, if this was like, here's my person, and then let's go ahead and draw some fire over here. Okay. The air in front of him is going to be near the same temperature as the air behind him. There's going to be slight differences, because the air on average is probably going to cool as you get further and further away from the fire. But more than anything, they should be, or the differences in temperature for the air should be pretty minimal. So while the burning wood does heat the air and the surrounding air, and it expands as it comes into contact, the main difference is he is seeing the light, the EM radiation, the infrared photons strike his body for D. Okay, so if we look at this, we're pretty much at our last question here. And so they ask, an ideal gas is confined in a container with a movable piston. The graph of pressure as a function of volume shows 4 different processes in which the gas is compressed. Which of the following correctly ranks the magnitude of the work done on the gas in the 4 processes? So in this case, they're all compressing the gas. The volume is decreasing. And so we have to try to find out, well, in which of these processes is work going to be the greatest, and in which of these processes is work going to be the least, and so on and so forth. So we have learned that the work is the area under the graph. And so if we look at 3 and 4, the work in process 3 is going to equal the work in process 4 because they have the same area. It's like 2 and maybe 3 squares in total. Yeah, so these guys are going to be about 3 squares in total. If we look at process 2, that's going to be 1 for this guy. That's 1, 2, 3, 4, 5, 6. This guy can go up there, 7 and a half-ish. And so I think process 2 is going to be greater than them. The work in process 2 is approximately 7.5 squares. If we look at process 1, the work done on the gas by process 1 is going to be the area under process 1, which would be all of this. And there's 1, 2, 3, 4, 5, 6 and a half. Oh, sorry. And then this guy is about 6 3/4. I'm going to say that this is about 7 squares of work or area. So from this, I think work done in process 2 is greater than 1, but those will be greater than the work done in process 3. The work done in process 3 and 4 is about 3 squares. Okay, so that just about does it for today. Thank you for watching. Have a good one, y'all. Take it easy.